Thank you for my introduction. Good afternoon, my name is Emily Webster and I'm a research scientist in the Mass Metrology group at the National Physical Laboratory in Teddington in southwest London. I joined MPL about 18 months ago, and since then, amongst other things, I've been contributing to a project which is supporting the international effort to redefine the SI unit of mass, the kilogram. As you may have heard, about 12 days ago, a vote was held at the 26th International Conference of Weights and Measures in Paris, and the decision was taken to update 4 of the SI base units, including mass, to fundamental constant definitions. These changes will come into effect from May next year, and today I'm going to speak a bit about this revision of the SI system, why it's necessary, and the potential impact and benefits of these changes. In a slide or two, I'm going to talk about a paper that hit the headlines in 2016, but first of all, I'd like to start out with a statement about metrology. So, the only way we know anything about the world around us is by measuring things. Metrology, or the science of measurement, is key to our understanding of the world and the universe around us. It's measurement that makes science scientific, not maths. Maths is great for distilling our understanding into a form that is straightforward and elegant, but it's measurement, the ability to compare an unknown quantity to a known standard quantity, that allows us to make any progress as a society. That said, in 2016, Monia Baker published a paper in Nature highlighting the reproducibility crisis in science. According to her survey of over 1,500 researchers in a variety of different fields of scientific research, 90% of them agreed that there was either a slight or a significant reproducibility crisis. So what does this mean exactly? Well, looking in a bit more detail at the responses to the survey, we can see that more than 3 in 5 researchers were unable to reproduce someone else's results at least once during their career. An even more troubling statistic is that more than 2 in 5 of them, across all fields, admitted that they couldn't reproduce their own experimental results at least once in the past. However, the majority of these researchers also say that they still have faith and confidence in the published papers, despite their own experiences with attempting to reproduce experiments. Perhaps this is due to the fact that the majority of them, around 2/3, reported that they already had established procedures in place to address this issue. So people are aware of it, and we are trying to make some headway in lessening this crisis. Well, why does it matter? Well, the last slide paints a rather confusing picture and clearly shows the need to get the situation under control. For those outside the scientific community, it doesn't do much for trust or confidence in science, or emerging science and technology. As a scientist myself, these findings make me think twice about the results I read in papers. And this type of doubt has a knock-on effect on the speed of progress in research, as many more tests and repeats need to be carried out in order to build sufficient confidence in our findings, and this takes time. So consequently, this means that the total time to implement changes is increased. Good metrology has an important role in helping to lessen the reproducibility crisis. If we are confident that we've made our measurements correctly, we can focus on other aspects of experimental design to find out why results don't appear to be reproducible. Meaningful measurement requires a traceability chain, such as what we can see in this pyramid here, which means equipment at the bottom of the pyramid has been calibrated or checked against a standard of higher quality, which in turn has been calibrated against a standard of higher quality than that, and so on. This continues all the way up to the top, which is called the primary realization. And this is carried out at national measurement institutes such as MPL, where a direct comparison to a unit definition is made. And it's only through traceability chains such as this that we can be confident in our measurements. In addition, for comparisons to be meaningful, it's imperative that they're all related to the same system of units. And the existing international system of units is formulated as a small set of base units from which all other units can be derived, either as products of powers of the base. The current definitions of base units were chosen for both stability and the quantity chosen, and the ability for the definition to be implemented in practice. That just means used in the real world. So if we had some quantity x, say the length of a component, and if we made the measurements, say in Australia, and then some measurements were also made in Nigeria, and both are traceable to the SI standard, then that means the two sets of results can be meaningfully compared with each other. More than 60 countries worldwide use the SI as their official system of units, but what if these definitions are inherently unstable? The definitions have been developed over time, since the late sort of 1700s, and with each redefinition, the focus has been on providing more stability using the technology and knowledge available at the time. The kilogram is in fact the last artifact-based definition, and we know that over time its mass appears to be changing. But we can't prove definitively if it's gaining or losing mass, because by definition it's always a kilogram, and all other masses in the world are relative to it. Thankfully, science and technology are now in a position to update this definition and bring it into the 21st century. As I mentioned, in the past, humans have come up with definitions of units based on quantities that were convenient to use at the time, so for trade purposes, or perhaps in the case of the pharaohs, to ensure that your pyramids are built correctly and don't fall over. In more recent years, we've used the unit definitions of the SI to measure the fundamental constants of nature. But as long ago as the signing of the Meter Convention in May 1875, it was known that the properties of atoms and fundamental constants of nature could also make a good basis for the system of units. So we realised that it's foolish to continue to measure something that is a constant against definitions that are based on unstable artefacts. So moving forward, we are going to turn this process on its head. We will fix the values of the constants and then use those to define the SI base units. We can then realise measurements based on definitions that have guaranteed stability. The other benefit of this is that the limits of our measurement capability will no longer be bound by the definitions. Instead, they will only be limited by the technology used in the primary realisation, and as the method of primary realisation will not be prescribed by the definition, these realisations are free to change as science and technology advances. So this is the general model that was agreed a week last Friday at the 26th CGPM. And from May the 20th next year, World Metrology Day and the anniversary of the signing of the Meter Convention, the new definitions based on this model come into force. So we have a new image for our modern SI. These are the values, in case you're interested, of the constants that were agreed to. These constants are expected to last for the foreseeable future, if not forever, with the possible exception of the second. Optical clocks are the focus of research for future definitions of the second, and once a consensus has been reached on the atom and the transition frequency to be used, that particular definition will be updated, and it will have a filter down effect to the other units that also use part of the definition of the second, but it won't be necessary to change those, only the second. Focusing on the biggest change that's been agreed, I'm going to have a quick look at mass. So historically in the metric system, mass of a kilogram was related to the weight of water in a standard container of about a litre. This sort of made sense, as pure water was relatively easy to get hold of, but there were a few drawbacks. such as evaporation and stability of your litre of water, and also water changes density with temperature. So it's decided to convert this weight into a platinum kilogram. So there we are. So, and then after the signing of the meter convention, we've got the kilogram that we use today was introduced, which is platinum iridium, and is stored in a vault in Paris. And that's what all masses are related to today. However, there are issues, as I mentioned before. We're not convinced that the kilogram artifact is stable, so we're switching to a quantum constant of a definition based on the Planck constant. And once we have the redefinition, there will be two ways of realising a kilogram. So traditionally, this is how we measure 1 kilogram in comparison directly with another one. And in the future, we will use the Kibble balance, which has, instead of a standard mass, it has a magnet and coil assembly on one side. Gravity pulls your test mass down, and then the magnet coil arrangement produces a force upwards to counterbalance the gravity pulling down. And if you can measure the current, and you have knowledge of a fixed Planck's constant and a couple of other electrical measurements, you are able to get mass directly. You no longer need to calibrate your balance with an artifact. Another way of doing it is also with a pure silicon sphere, but I haven't got time to explain all the details of that, but there is another method. So, a bit more now about Kibble balance technology. This is NPL's next generation Kibble balance, and it's aimed at National Measurement Institutes for primary realisation. So this is right at the top of the tree of the measurement chain. The original Kibble balance was based on the traditional twin pan balances, as shown in the earlier animation. This is our next generation, and it's a unique design based on seismometer technology, using flexures to limit the movement in the z-axis, so up and down. The measurement coil and magnet are located at the base of the balance, sort of down here, and that is where the measurement current is applied, and it generates the additional force to counter your force from your test object, which is the silver sphere in the middle. But there's also an additional coil and magnet at the top, which provides the support for the central carriage when the balance is unloaded, holding the central carriage at the 0 point. The great thing about the redefinition and the Kibble balance is that it can be used at any point on the mass scale, which removes the need for a process called subdivision. At the moment, we have to move from a kilogram and step down using groups of weights, so a kilogram compared with 2 500s, and so on, all the way down to milligram. And this graph is showing that the relative uncertainty by the time you get to a milligram is coming up to about the same size. It's significantly larger relative uncertainty at small mass scale. Whereas with the new definition and a Kibble balance, if we're able to scale it, there'll be no need for subdivision, and we will be able to put masses directly onto the Kibble balance and have a directly traceable measurement to the new definition. This will significantly reduce uncertainties at these levels and will open up opportunities for progress in pharmaceutical research, personalised medicines and medicine delivery devices. So, for example, development of treatments that require micro or even lower dosing will be able to make much faster progress, as the level of uncertainty on the measurements will be no longer prohibitive. Here are some concept designs of a miniature Kibble balance. This sort of technology could be embedded directly into devices in the future. They will require calibration for their electrical systems, but the need for check masses will be removed, saving time and money. It's also possible to remotely calibrate electrical systems, so this could also be useful in areas where it's hazardous to enter the environment where the device is. Okay, so in summary, there is a recognised problem with reproducibility in research, and there is a global effort to increase the reproducibility of scientific research published in the future. The redefinition of the SI is a key part of ensuring this global goal is met, and the new SI will be a solid foundation on which to build future advances in science. And in particular, the new quantum definition of mass will allow measurement uncertainty at low, so sort of milli to micromass scales to be reduced via Kibble balance technology. Okay.